Hi, everyone. My name is Tom Broussard. It's nice to see everybody. Beautiful day here in Maine. This scientist is Karl Lashley, another one of these scientists who have come to approach to attack one part or another of the brain. And in this case, with Lashley, he has been studying about how the messages, how the stimulus, how the activities get into the brain. Basically, how do they get in there and stay there? So he was doing all kinds of experiments, and another person had invented a word called Engram, which is basically it's where in the brain something lands, some stimulus lands, the information lands and gets engraved so that it stays there. So that's what they're trying to figure this out. And Lashley ended up calling it his search for the engram, because he continued to look for that, because there had to be a way to get information into the brain and have it stay there, have it be engraved there, basically, in the brain, somewhere in the cells. And a lot of people in the beginning thought that memory was such that it landed in a place like in a drawer. You open a drawer, put it in and close it, and it stays there. So that's how it all was, the beginning of this. But as Lashley was working on it, he began to realize that it's not made that way. Memory doesn't just stay in one particular place. It's really diffused throughout the brain. But of course, when this first scientist, a guy named Richard Seaman, he's the one who wrote about it, studied about it, and coined the word engram. He had said that he's trying to trace resect pathways through the brain, and to find the locus of specific memory traces. So that's what he was doing with this engram. And he said, I'll read this. This I call the engraphic action of a stimulus, because a permanent record has been written or engraved onto the irritable substance. I use the word engram to denote this permanent change wrought by a stimulus. So Lashley has been working with this, and been working with rats, little mice, basically, and studying their behavior if they train them a certain way, and then now that they have what they didn't have before, so they'd learn something, and then being to see where they can find that in that the body of the brain of the mouse's memory. But as he continued to do the experiments, which means he would obviously kill them, look at their brain, take out pieces of the brain, I mean, before even killing them, taking out pieces of the brain to see if they could still learn. And as he did that, the more he saw that no matter how much he was removing where he thought the memory might have been, the mouse still remembered. And that's when he began to understand that something, not wrong, but his theory with the engram doesn't seem to be working, because he could not find that pathway, that if the stimulus comes in here and here and here, and then goes into the brain and then makes its way. As we now know much more about the integrative capacity that the brain has, basically bringing all this stimulus in and then has to integrate all that information. So it has to put it all together and put it back out again all over the brain. He couldn't find a particular pathway. And as he was continuing to trace the tracers, he ended up saying, and I say here, conditions or memory traces are either diffused through parts of the body, through all parts of the cortex, pass by relay through lower centers, or do not exist. So that is him studying this for decades, and came to the conclusion that I can't find it. I can't find that engram. But as he continued to trim off more and more and more of the brain of that little mouse, literally he cut down to 1/60th of the functional area of the brain of that little mouse, And yet at 1/60th left, he could still know. He knew what that was. He could see what it was. He knew what that was. And that means, how could it be that all that, quote, memory was in one particular place, since he was now cutting off what he thought was the memory component, cutting off more and more and more, getting to 1/60th, and the mouse could still remember and could still see what it meant to see. So that's when Lashley decided that it really is not located in one very specific place, but are distributed throughout the functional cortex area of the cortex. So that was pretty interesting, more than a little interesting for me and for you to begin to realize that as much as we have some places in our brain that we call our memory core, and amygdala is one of them, but still the brain is so powerful, memory is so powerful, so many stimulus are led to memories too, whether it be the smell or the taste or feeling. We begin to realize that the brain, being that powerful, actually can hold a tremendous amount of information, even within small components of it, cells or groups of cells scattered throughout the brain, such that the redundant component of the brain is another part we have to continue to study, because there are so many ways that once certain parts, obviously from a stroke, are destroyed, the brain still has that capacity to grow and use or reuse the turf, as they talk about it, of the brain that's still healthy, and use that to do what the other part that's now gone used to be able to do. So how does that happen? Well, there are plenty of people, I've met some of them, who have lost half of their brain, and yet, and either half, and now can read, write, and speak very, very well. If you didn't know, you wouldn't necessarily know that they had lost half their brain. Why is that? Because again, the brain is incredibly powerful. Whatever we think we say when we say it's powerful, times 1,000. It is more powerful than that, because it has developed itself, of course, over millennium, over evolution, such that the cells have this capacity to grow new brain matter, new dendrites and synapses, basically creating new connectivity. And that's where everything happens. That's where all learning happens, is at the synaptic level, the learning field. As Lashley continued to study this, he, among other things, he came up with an understanding that the number of connectivities really is the most important part of the nervous system. It's the connections, what we call the C's, in the brain, that where the synapses happen, where they make the connection between one cell and another, one neuron and another. It really comes through the synapses, with the dendrites and the axon, and then the cell is down here. So you can't get to it this way, you get to it this way. And sometimes you can get it this way, but they have actually synapses up and down the dendrites too. So it really is the number of C's, and what they have at that time. And that is where the proportional understanding is, that if you lose X number of C's, not necessarily the neurons, but obviously that's what matters, because the neurons hold the C's, they uphold the C's. But if you remove or are damaged from a stroke and you've lost X amount of C's, then that is the issue, because then you can grow new C's. You can't grow new neurons. There are some places in the brain where you can actually grow new neurons, new cells, but not in the frontal part. The thinking cells just have the cells they have after the stroke, but they can grow new dendrites and synapses. That means they're growing new seeds. So people with aphasia have lost millions of connections, but the remaining healthy cells can grow new connections based on persistent and repetitive language activity. It is all about the C's, if you can understand it in that way. So I like that a lot. I've made some new slides to go into my presentations referring to the C's, because originally when I knew that we lost a whole bunch of neurons, as you would know too, you've lost your brain cells, I thought that was the equivalent of what had happened. So that X of this would mean X of this in terms of the damage, behavioral understanding of that damage. But it's really about the C's. So you can have one neuron and literally, you can have 10,000 C's, 10,000 synapses. And that means that's each of them is a seed, is a C. Or you can have a neuron that only has a few thousand C's. So it's really, yes, the cells go. It's really about counting, not like we can count, but it is all about the C's. That is where the learning field had made the messages they were providing before at a certain amount of speed. They're now gone. Now you have to regrow them and develop new seeds going forward. So this particular thing, although Lashley said he was very upset that he couldn't figure out that he could find the Engram when he found out that you really can't find it that way. There is no Engram, really. There isn't one place that just sits in a drawer by the way the brain works, but they are dispersed throughout the brain. And as he began to understand that, now we get to see it as well. So he did a lot of work to do this. And so we have to applaud him for all of his work as we continue. For all of us who happen to have stroke and aphasia, that provides us, you and me, with a lot more information about how the brain works than most students and healthy people, unless you're a neuroscientist or some kind of scientist. At the next level are people like us who actually experience what it feels like to have lost X amount of brain matter and now, quote, get better, because most of us do get better. It's just a matter of how long it takes and how severe it was in the brain and where it was in the brain. But all the people I know do get better, even if I know and they know that they desperately want to continue to improve better enough to be much more what they used to be. So that is what my path is on, is helping find these scientists and then helping their decades worth of work and help. And I'm trying to help explain in all of their work over many, many decades to condense that into enough for all of us to now understand at least a little bit better about how the brain works when it rewires itself. So Karl Lashley, another very interesting scientist. Thank you very much. I'm looking forward to the next one. Nice to see everyone. Take care of yourself. See you soon. Bye.